Hello there, Mr. Sutton with a lesson on domain, range, and functions. In this one, we'll be figuring out domain and range and determining if a relation is a function or not. And while we're at it, we're going to find intervals of increase and decrease for functions and evaluate functions. For our first warm-up, we're going to start by seeing if you remember how to write things in interval notation. Here are 5 expressions in standard inequality notation. Pause the video and see if you can convert these. All right, let's see how you did. So for this first one, remember with interval notation, we're always writing these inequalities as the first number comma the second number, basically saying what two numbers all of our stuff is between. So this would be 1 comma 6. But now we have a parentheses and we have a bracket. A parentheses, a normal parentheses, goes where you don't have equality. Like with this 1, x cannot actually equal 1. So we would go parentheses 1, comma, and then if you have the equals here, we use a bracket to show that 6 is part of the solution. So parentheses 1 comma 6 bracket. All right, on this next one, we're going from the far left to 5. So 5 is going to get a bracket. It's going to be something comma 5 bracket because it equals 5. But now what's the first thing we're going to put in there? Well, if we're going left forever, that means that we're actually going to negative infinity. And we're always going to put infinities with a parentheses because you can't ever actually equal infinity. For the next one, it's kind of the same deal. Now we're going from negative 8 with a parentheses, comma, positive infinity because we're going to the far right, which, you just keep going. For this next one, we've got negative infinity, comma, negative 3 in a parentheses. Or, so instead of writing or, to do this fancy in interval notation, we put a u, bracket negative 1, comma 4. So you just do each inequality individually and then link them up with these u's to show that they're all part of the same solution set. And then finally, all real numbers, we want to go from negative infinity to positive infinity on this one, all parentheses. For our second warm-up, we're going to go over some of the definitions you've probably already seen on function stuff, but just to make it fun, pause the video and see if you can match these up with the correct definitions. All right, so a relation. A relation is E, that is a pairing of inputs and outputs. And this can take the form of a table, just a bunch of points written out, a graph, an algebraic function, any of these. Domain is all of your possible inputs, all the x values, so C for that one. The range is kind of the same idea, but with all the outputs or y values of a relation. A 0 is an input whose output is 0, a root or an x-intercept. These all mean the same thing. And then a function, that is a relation where each input gives only one output. So for something to be a function, when you plug in an input, you should keep getting the same output. You shouldn't get a different output every time you plug in the same number. So part of what we want to do today is to be able to pick out some key features from a function on a graph. So for this one, we want to find the domain and range of the graph, then tell whether it's a function, and if it is a function, identify intervals where it's increasing, decreasing, and constant. So let's start with domain and range, because we're going to have to do that regardless of whether it's a function or not. Domain is all the inputs, all the x values. So for domain, you're basically looking to go from the far left to the far right of the graph. So the furthest left we can go for x values is negative 1. The furthest right we can go is, let's see, this is positive 5. And we have to keep track of whether the endpoints are actually part of the graph. So if we have solid dots, we include them. This, for example, would be bracket negative 1. And I'll put a little d here for domain. Over here, we've got a 5 with a solid endpoint. So that would be bracket positive 5. So we're going to do the same idea for the range. The range, we're going from the bottom to the top, because that's all the y values. Pause the video for a sec and see if you can write the range of this graph. So hopefully you came up with bracket 0, because that's the lowest y value and it's included, comma, bracket 2. Now you might be saying, well, there's no dots up here, but if it's a solid line, it also counts as like a bunch of solid dots. All right, for the next thing, we want to know if this is a function or not. So a function, remember, that means that every x value gives you only one y value back. Now, a quick way to check for that on a graph is using the vertical line test. Vertical line test, you're basically running a vertical line across the graph, and if at any point your vertical line touches the function or the graph twice, then you don't have a function. So, for example, if we had a vertical line that we drew right here, and it touched the function here, and let's say there was another dot up here, that would be saying that we had an x value that gave us back two different y values. If you have two parts of the graph on the same vertical line, then you don't know which y value you really want back. So let's run that vertical line across here. So here we go. And are we touching twice anywhere? Nope, it does not look like we are. So if you don't touch twice anywhere, that's a good thing. That means we passed the vertical line test, and this is indeed a function. Now, the other thing they wanted, if it is a function, they want to tell where the function is increasing, decreasing, and constant. So increasing, if you weren't sure, means that as you move to the right, the graph is going up, and that's important. We're always talking about as we move from left to right on this. So think about slope. You know, if you call slope positive or negative, we're talking about as we go from left to right. So our first interval, where we are going up, this very first interval from -1 to 0. So we would write -1 comma 0. And in case you're worried about it, with these increasing, decreasing kind of deals, you can always use parentheses. There's actually debate in calculus circles whether or not you should include these crossover spots in the interval or leave them out. We're going to leave them out. So let's keep going. Where else are we increasing on this graph? Oh, well, from +1 to 2. So we would write union 1 comma 2. All right, so decreasing now. That means going down. Pause the video and see if you can write the intervals where we are decreasing on this graph. Okay, let's see how we did. So we're decreasing from 0 to 1, so 0 comma 1. And we're also decreasing at the far end here from 4 to 5, so union 4 comma 5. And then finally, constant. This is where you have a horizontal line that is neither increasing nor decreasing. It's just the same y value as you plug in more and more x values. So that's going to be this little spot right here from 2 to 4, so 2 comma 4. And again, you can always use parentheses on these intervals of increase and decrease, and it'll be just fine. Here's another graph for you to try out. Pause the video and go through the sequence here. All right, we'll start with domain. Now from domain, we're going from the far left. We just keep going left forever, and then we go right forever. This part of the graph stops, but we have a piece of the graph that is going left forever, so that's all we need is just one piece. And we're going to use infinity to represent going forever. Makes sense. So our domain then, you should have -infinity comma positive infinity with parentheses. For the range, well, the lowest we can go on this one is this open dot down here at -2. And as far as going up, we're going up forever. There is one little sneaky piece here, though. And that is, as we get closer and closer to the x-axis, we never quite get there with this graph. So the y value 0 is also not in our range. Our first interval, then, we're going to have parentheses -2 comma 0, because we can't actually hit 0 here. And then we're going to have to union that with 0 comma positive infinity, because we just keep going up. And now for function, let's do our vertical line test. As we run it across here, we see this is very clearly touching the graph twice. And this is an issue, right? If you plug in -3 for the x value, well, which y value am I supposed to give back? Is it, this thing that's close to -2 or +2? We don't know. We can't decide. So this is not a function, fails the vertical line test. And if it's not a function, we don't have to tell increasing, decreasing, or constant, which is a good thing, right? Because, this interval here, am I increasing or decreasing? Well, it depends what part of the graph you look at. We're going to shift gears a little bit to talk about f of x notation. This is how we represent functions algebraically. So this table here gives us some x values and some values for something called f of x, and they want us to find f of 2. Now it's important to note this is f of 2, not f times 2. This is not necessarily multiplication. So the idea with this f of x notation that we can write functions in is that we have some input that we're plugging into this function. These are the domains that we were talking about earlier, the x values, and the function gives us back an output. This is what the function returns from the range. Either you could call it a y value or you could call it f of x. They're really interchangeable. So if we just represent this visually, we've got some function which does something. We have inputs over here that we're plugging into the function, kind of like putting something in a machine, and then the function does some crazy magic in there. Now what exactly is the function doing to our input? Well, it depends. Functions can be defined with either a table, a graph, or a formula. Here is a table defined function. We'll take a look at graphs and formulas later in this lesson. With a table, all you have to do is look up the given x value. So we're asking for f of 2. We look up 2 in the x row, which is right here. And then you just have to return the y value that goes with that x value. So looking at this, we see that it's associated with a y value of 5. Why? Well, that's because we set it up that way. So that means we're just going to return 5 up here out of our function. So we plug in 2, we get back 5. Now, to represent this algebraically, we can write f of 2 equals 5. The input to my function is 2, the output is 5. The value of my function at an x value of 2 is 5. Any of these ways of representing it. Taking a look at this next problem, another way of representing functions is with a graph. And they say a picture is worth 1,000 words. I mean, rather than writing a whole bunch of x and y associations, you can just draw them all out here. So to do things with a graph, all you have to do is find the point on the graph that has the given x value, and then give back the y value of that point. So if we're looking for f of 5, for example, then we just have to look where the graph is actually on the x value 5. So we go over to the x value 5, which is right here, and look at our graph, and we see that our graph has a point on x equals 5 if the y value is negative 3. So we would just say f of 5 equals negative 3. Pause the video and figure out f of negative 4 and f of negative 8. All right, let's see how f of negative 4 went for you. So the x value, negative 4, right back here, that has a y value of 1, so f of negative 4 equals 1. And for f of negative 8, we look at the x value, negative 8. So this was negative 4, 5, 6, 7, 8. And let's check where the function is there. Oh, we have an open dot. Well, what does that mean? And here's where we have to be careful, because the x value may not always be defined on the function's graph. There may not be a solid line or dot where you're looking up the y value. So in cases like that, we would write, for example, here, f of 8 is undefined. So now we're going to take a look at evaluating functions with formulas, and we're going to do this in the context of a real-life problem. Let's say you're saving up $500 from a summer job, and during the school year you find a pizza delivery job that pays $7 an hour. So your total money is shown by the function below, where x is the number of hours. So we have $500 from your summer job, $7 per hour, each hour is an x here. If you do 7 times the number of hours plus 500, you should get how much total money you have. So let's say you work 800 hours over the school year. How much money are you going to make? So we have a formula for how much money you've made, and we want to plug 800 into that formula. So this is a real-life function here. So let's go ahead and evaluate this now. Woo, that was fancy. Oh no, you got to look out for those falling pizzas. So here's the problem we were just looking at. If we have f of x equals 7x plus 500, we want f of 800. And just to really emphasize the point, the f of x does not mean multiplication. It's just telling us what to plug in for x and the name of the function. And it's important that we have this function name because there are problems where you might see more than one function, so you want to know which one you're talking about. So when you're doing this, you're just replacing every x in the formula with whatever expression you're plugging in And I would recommend you use parentheses when you do this. So if we want f of 800, we're just going to rewrite this as f of 800 equals 7 parentheses 800 plus 500. And then we just evaluate that as we normally would. So this f of 800, you could just think of this as y now. It doesn't actually do anything else for us. We're just evaluating the stuff on the right side now. So we've got 5,600 plus 500, which will be $6,100 that you've made after 800 hours. Awesome. All right, here's another one for us to try out. Let f of x equal a different function now, 3x minus 7. Find f of 6c minus 9. Now this one is a little bit goofier. Up here we were just plugging 800 in for x, and it was a pretty direct substitution. But what do we do down here if there's more than one thing inside the plug-in parentheses? Well, plug it all in. This is the advantage of using a parentheses when you plug in, is that you can put pretty much anything that you need to inside that parentheses. It is infinitely expansible. So now instead of writing 3 times x minus 7, we're going to write 3, erase and replace, parentheses 6c minus 9, all that minus 7. So again, the x is infinitely expandable. You can replace it with any expression that you need to in these functions. And now we're just going to simplify as much as we can. So distributing, we've got 18c minus 27. Still have that minus 7 out there we can't forget about. Negative 27 minus 7, that'll be negative 34. And that's our final answer. In general, if you're plugging something into a function that has a letter, you're probably going to get a letter in your final answer as well if it doesn't get canceled out somewhere along the way. Now that we've got the basic idea of plugging into functions, we're going to up the ante a little bit here. Pause the video and see what you make of this one, where g of t equals t squared, and we want g of n plus 7 minus g of 3. All right, so our strategy on this one is when we have multiple functions, we're going to evaluate each function call separately and then simplify at the end. So first we need to get rid of these g's and replace them with actual expressions that we can evaluate. So instead of writing g of n plus 7, we'll have n plus 7 squared, because this whole n plus 7 is taking the place of t. And over here, instead of g of 3, we're going to have minus 3 squared. Next, we have to simplify this. Now, I told you we'd be needing to expand binomials again. We didn't learn that shortcut back in the day for nothing. So expanding this now, you can either write this twice or use the shortcut. The shortcut, we have to square the first thing, multiply these two things together and double it for the middle term. So that would be 2 times 7n, which is 14n. And square the last thing, so that would be 49. And over here we have minus 9, giving us a grand total of n squared plus 14n plus 40. We'll do one more function problem here. In this one, h of x, now we can use h, equals 4x minus 1. We want to find the value of c for which h of 5c equals 139. So this is kind of confusing when you first read it. The idea here is that when you plug 5c into the h function and all that stuff comes out to 139, there's going to be some value of c that actually makes that true. So our first step is we're just going to plug 5c in as it is into this function. So instead of writing 4x minus 1, we're going to write 4 times 5c minus 1. Now when we do that, according to what they said over here, it's supposed to equal 139. So we're just going to replace this h of x here with 139 and set it equal. At this point, we have an equation. All we have to do now is solve for c. So add 1, and while we're at it, 4 times 5c is 20c. So we have 20c equals 140. And then dividing by 20, we get c equals 7. So that is it for our whirlwind tour of all things function related. Till next time, this is Mr. Sutton signing off.